Today we want to look at the fundamental theorem of calculus for line integrals. This came up yesterday, but we talked about a lot yesterday. So let's recap what we talked about. So the fundamental theorem of calculus has the following. I forgot to do all the lead into it, so I just started right with the integral part. But we got the integral over c of some gradient, the gradient of some function. Now the gradient of a function will produce a vector field. And it's got to be a function of x and y or x, y, and z for the I component, and a function of x and y for the j component. So the interesting part about the fundamental theorem of calculus says that if you integrate the gradient, a gradient field over any path from point P to point Q, it's just the difference in the potential function at the endpoints. So when you integrate a gradient field over any path from point P to point Q, you'll just get the difference in the potential function at the endpoints. It's just going to give you the change in the potential function. So we had an example of this in the problem from Friday. I gave you a vector field F. Our vector field F was yi plus xj. And we had two different paths from -1, 1 to 3, 9. So C1 is the line segment from -1, 1 to 3, 9. And C2 is the parabola y equals x squared with the same endpoints. Now, without the fundamental theorem of calculus for line integrals, we can calculate the line integral over C1 of this vector field and the line integral over C2 of the vector field. But we'll want to check if the vector field is a gradient field. If the vector field is a gradient field, then we get to use the fundamental theorem of calculus for line integrals. So we have these two line integrals to calculate. If the vector field is a gradient field, then we get to use the fundamental theorem of calculus for line integrals. So our thoughts: if the vector field F is a gradient field, then we get to use the fundamental theorem of calculus. We can use the fundamental theorem of calculus for line integrals. It kind of bothers me that this one doesn't have a name, or that I've never been presented with a name for the fundamental theorem of calculus for line integrals other than fundamental theorem of calculus for line integrals, because the two other fundamental theorems of calculus are called Stokes' theorem and the divergence theorem. It's like, oh, why do they get cool names when this one is just the description? It really kind of bothers me. It kind of bothers me that if I was told what the theorem was named, I'm annoyed that I forgot that. So I'm not sure what, and then that's annoying because I'm not sure how I'm supposed to be annoyed by this particular lack of information. Anyway, so one way to check if the vector field is a gradient field is to try to find a potential function, or we can check the second derivative, the mixed partials. So to determine if the vector field is a gradient field, we can either just find a potential function or check the second mixed partials. So what we might want to know is f a gradient field. We can either find a potential function, or B, check the second mixed partials. If the mixed second partials are equal, then we have a gradient field. In this case, we're going to look at yi plus xj, and we'll say that yi, that's the partial of f. If there's a potential function f, then the partial of f with respect to x is equal to y. That means that f, if we just integrate y with respect to x, f should look like xy plus some function of just y. That's what our constant of integration looks like when we have partial derivatives. Then we can look at x, the j component, and that would be the partial of f with respect to y. This would tell us that f should look like xy plus some function of x. And since I have this matching here, this xy, that must be what f looks like. Our g of xy would look like any constant, and our h of x would look like any constant. Remember, we're doing partial derivatives. Functions of the other variable that are terms will just be constants. So it looks like our gradient, our potential function, is xy. When we look at the function f, we have these two scalar functions for the components. So if our vector field looks like f, there's a scalar function f1 for the I component and the scalar function f2 for the j component. f1 is the partial of the potential function with respect to x. f2 is the partial of the potential function with respect to y. So we'll check if the partial of f1 with respect to y is equal to the partial of f2 with respect to x. So what we're checking is if the partial of f1 with respect to y is equal to the partial of f2 with respect to x. This is what we want to know. If the mixed second partials are equal, then there is some gradient field, some potential function, because the vector field is the gradient field. So the partial of f1, so in this case, f1, I didn't leave myself space, is equal to y, and f2 is equal to j. Sorry, the j component, which is x. The sentence is difficult today, don't know why. So the partial of f1 with respect to y is equal to 1, and the partial of f2 with respect to x is also equal to 1. Since these two are equal, the mixed second partials are equal, the vector field is a gradient field. There is some potential function sitting above all of this. So in this case, since our vector field is a gradient field and we know the potential function, we can just evaluate the potential function at the end points. So if I want the integral, since f is a gradient field, yi plus xj is a gradient field, if I want the line integral over c1 of f dot dr, I can just take my potential function evaluated at -3, 9, and subtract the potential function at -1, 1. So I'll just take 3, 9. I'm going to keep writing them as points because my function is just xy. Something was telling me that using this function was a mistake, but now I know why. So 3 times 9 is 27, plus 1 is 28. Just evaluate the function at, so we're thinking of -1, 1 as the function p where we start, the point p where we start, and 3, 9 is q where we're ending. So here is f at p minus f at q. We're just looking at the change in the potential function. I did it backwards. F at q minus f at p. Yes. Correct. So since we're dealing with a gradient field and the endpoints are the same over here, I could have written here. Oh, well, it's icons. The integral over c2 of f dot dr, since f is a gradient field, the field is path independent or conservative. Conservative is what we call path independent. We'll just get the same thing, 28. Because we checked and found out that the vector field is a gradient field. One thing I want to point out is that up here I wrote C is any path from P to Q, and that is because gradient fields are conservative, that is path independent. Conservative and path independent are the same thing. And I also wrote underneath that conservative vector fields are gradient fields. So one is the other. Those things are the same. Because sometimes we do different things, like a differentiable function is definitely continuous, but not every continuous function is differentiable. those two conditions are not equivalent. But if you want to find out if a vector field is conservative, check if it is a gradient field. Path independent is a more descriptive thing, but conservative is a more general way to describe what's going on. You want to think about things like conservation of momentum, conservation of mass, conservation of energy. It's that kind of conservation. That's why we call it a potential function. We're looking at Q minus FP. That's the difference. That's the change in the potential function. That's as far as I want to go with my crappy physics explanations for things, because I am not a physicist. I wonder sometimes if any physicist reads like the physics examples in calculus textbooks and says, man, these are kind of weak descriptions of this physics stuff. You know, a bunch of mathematicians, they're like, oh, well, we have to do this because your math is terrible. Any questions? Normally I've had some coffee before I left the house, before I get the coffee that I carry with me throughout the day. It's not that I'm an addict or anything. I can quit whenever I want, but might be why I'm struggling today. So I didn't have coffee before I left the house. All right, so I have one other thing that I want to go, two other things that I want to go over today. Number one is that this fundamental theorem of calculus fits the mold of the fundamental theorem of calculus that we had way back when. All of the things that we call fundamental theorems of calculus are going to fit this structure. So if you recall our original we're abbreviating everything. If you recall, the original fundamental theorem of calculus from single variable calculus, Calc 1 and Calc 2. I'm going to leave off the prelude stuff, but it was the integral from A to B of f prime of x dx is f at B minus f at A. We integrate the derivative of a function over an interval or over a set by evaluating the change in the function at the endpoints of the set, at the boundary of the set. We integrate the derivative of a function over a set by evaluating the change in the function at the boundary of the set. We integrate the derivative of a function over a set by evaluating the change in the function at the boundary of the set. The endpoints A and B form the boundary of the interval from A to B. We are integrating over the interval from A to B. So in this case, the set is the interval from A to B. The boundary of this set are the 2 points, A and B. This is the structure that we're dealing with when we call something a fundamental theorem of calculus. If we look at our fundamental theorem of calculus for line integrals, now I'm bothered that there is a fancy name for this and I just can't remember what it is. Damn it. If there isn't, I'm going to have to check if there isn't, because I'm going to say that it's Leach's theorem. It's like, well, how could the fundamental theorem of calculus be named for some dude from the 20th century? And then they'll be like, oh, well, he was American, so he probably stole it. Oh, yeah, that tracks. You know what I mean? I wonder if I could do that without any money. That'd be the best. So in this case, in the fundamental theorem of calculus for line integrals, the set over which we are integrating is any path from point P to point Q, and the boundary of that set. So here's our set. And the boundary of that set is just the endpoints, P and Q. Now, the other part of the fundamental theorem of calculus structure is that we integrate over some set the derivative of some function. So in this case, the gradient is standing in for the derivative. The gradient of f is the derivative of the potential function f. So the gradient of f is the derivative part. And I'm going to put derivative in quotes. Yeah. Never seen it referred to as just the gradient theorem. That's really annoying. It's Leach's theorem now. Look at me. Look at me. This is Leach's theorem now. Just kidding. I think it's just the books that I learned calculus from called it the Fundamental Theorem of Calculus for Line Integrals. The book that I started teaching Calc 3 out of called it the Fundamental Theorem of Calculus for Line Integrals. So I just started calling it that. And I'd have to search all the way back to like 1990 when I was learning Calc 3 to try to remember. I've also been in this one book that calls it the Fundamental Theorem of Calculus for Line Integrals for 20 years, so I'm not surprised that it's just the gradient theorem. That pisses me off. I'm going to name it after myself anyway. So in the gradient theorem, the gradient is standing in as the derivative. That's what we would have like in the original Fundamental Theorem of Calculus with the f prime. And so we're integrating over this set, which is any path from point P to point Q, the derivative, which is in this case the gradient of the function, and by just evaluating the potential function at the endpoints and looking at the difference. Oh, I have it backwards up here. Holy shit. The coffee is starting to hit, so I'm starting to realize how much I was writing without paying attention. And no one said anything. That's minus 1,000,000 points for everybody. Because I wrote from P to Q, so I have to do FQ minus F of P. Like I said, minus 1,000,000 points for everybody. That is 1,000,000 points collectively for the whole class. So if someone has lots of points, they might want to contribute more, absorb more of the negative. I always wanted to experiment with that. Make classes a little more collective. Like, your score on this test will be whatever score you got on the test, and then you get a second score, which is the lowest score in the class. Or just add up the total number of points earned by the entire class, and then allow you to share them. Well, they could do that, or now you could do it American style and get mad at the people that scored low on the test and try to get them kicked out of the class, or you could try to help them score better. And then I would not only be able to judge your ability in math, I would be able to judge you based on your character as a human being. The second option, encouraging helping the whole group, that's what I would be going for with that scheme. So spot on. But it's a difficult thing to do in math class, like because you could collectively, like if you have a teacher that grades on a curve, you could, if the class was willing to cooperate, then you could kind of game that system. Like, so instead of students scoring very high, and so they say wrecking the curve, I'm not sure even students really understand how wrecking the curve works. It kind of inflates the average. It inflates the average. So if everybody gets a 70 and then like 5 students get 100, then the average is going to be higher than 70. But if 5 out of 100 people are taking a test and scoring 100%, and everybody else is getting 70, then it doesn't make sense to include those in the average. Yeah, the average is higher, but is that higher average really representative of the performance of the class as a whole? I'm talking about like a large class. If there's only like 10 people, then none of this applies. So if the teacher's like, oh, no, if you got a bunch of students that are getting really high scores and they're raising the average, so that makes your average score, which is really representative of the performance of the class, look worse because of the high performers. What you need to do is get together as a class and all agree on some maximum score that you're all going to get. It's like, oh, dude, we can all score 70 on this test, so let's all just agree to score 70 on the test, and then we'll all look better. But then the teacher will be like, oh, now everybody gets a C. And the A students are like, oh, now my parents will beat me up if I come home with a C on a test. Someone always breaks, is what I'm saying. See also the prisoner's dilemma. One of my favorite facts about cooperation, I don't know if anybody has seen the movie A Beautiful Mind, but one of my favorite facts about cooperation is we have this dude that writes this paper and says, you know what? we would all be better off if we would just cooperate. Now, the way they demonstrated that in the movie is really sexist and gross. Yeah, with Russell Crowe. It's really sexist and gross, but I guess it illustrates the point pretty well. It's like, well, you know what? If we cooperate, then we will all be better off. And everybody's like, oh, fuck yes, that's a great idea. Give that dude a Nobel Prize in economics for showing us that cooperation is the way. And then everybody else be like, oh, great. Does that mean we're all going to cooperate now? And America went right back to, nah, fuck you. I'm going to get mine. We would all be better off if we cooperate, but we're not going to do that. Because this is America. Fuck you, pay me. That's America's model. We should put that on the money. What did I learn in group work? How to work alone. That's true. My whole philosophy was when I was in group work, I would find the people that did not want to do anything and just do all the work for the group because I didn't trust them. So. Also, as a student, I would perform some inadvertent group work. I got 5 A's in high school chemistry. I got the 1 A that I got and the 4 A's of the dudes sitting around me during the test. In geometry class, I was a freshman in high school and in geometry class. And so I was like the only freshman in the class. And so it was kind of intimidating because they're like juniors and sophomores there. And I'm just a weedy old freshman. And so the geometry teacher just kind of sat at the front of the class and said stuff and then eventually gave us a test whereupon he just sat at the front of the class and sometimes just kind of fell asleep. He was old and close to retirement, and he was really there to coach football. It's that kind of thing. So we're like sitting there taking a test at one point, and some dude across the room, where I sat at the back of the room, and somebody at the other end of the room, sitting in the back row, actually airmails me a question on the test. So I'm like sitting there just filling out my test, and all of a sudden, a wadded up piece of paper like lands on my desk. It's like all, and I'm like, oh, what the fuck is this? And I like pick it up and I like look around and then there's a dude looking at me. He's like, oh, hey, and he like points to it as if I should open it up. And I open it up and it's a crumpled up piece of paper that says, what is the answer to number 2? I go, did you just ask me to cheat via airmail? We didn't have phones back then, so he couldn't just text me. So that was part of it. Anyway. I did. I mean, I was trying to be cool, right? I would do it again, too. If we're not going to help each other, what's the fucking point? All right. It seems more radical back then than it does now, because back then this was America and this was the 80s. And we had to win against the commies. I was subject to a lot of propaganda. See, like this generation has like a lot of secondhand propaganda that they got from their parents because the propaganda was really effective on their parents. And so they just pass that on to you. More importantly, in the gradient theorem, I'm already doing it. In the gradient theorem, it's the structure of a fundamental theorem of calculus, which is the real reason we do this. It's the structure of the fundamental theorem of calculus. We integrate the derivative of a function over a set by evaluating the change in the function at the boundary of the set. For a function of a single variable, the set is very simple. It's just an interval from A to B. It's just an interval. And the boundary of a set is just the point A and the endpoint B, just the 2 endpoints. In the case of the gradient theorem, the fundamental theorem of calculus for line integrals, we've got the set over which we're integrating is any path from point P to point Q. And those endpoints serve as the boundary of the set. So it's very useful that the vector field is path independent. Any questions? The other thing that I want to think about today, I just want to put that out there as a thought. Think back to Calc 1 where we had function, first derivative, and second derivative. Function, first derivative, second derivative. Think of all the information we got when we were looking at a graph of a first derivative. We could use that to make inferences about the second derivative, which told us about the concavity of the function. So think about the first function, first derivative. The sign of the first derivative tells you about the direction of the function, where the function's increasing and decreasing. The direction of the first derivative tells you about the concavity of the function. The sign of the second derivative tells you about the concavity of the function, tells you about the direction of the first derivative. That hierarchy, that relationship between function, first derivative, second derivative. Look at what we're looking at here today. We're looking at a vector field, which is a gradient field, which is acting as that first derivative. Function, first derivative, second derivatives. Now, if we look at these two, we got the partial of f1 with respect to y and the partial of f2 with respect to x. We combine those two into what we call the curl. That'll be the scalar curl for a function of a vector field in R2. So that's our hierarchy. We still are looking at the hierarchy with function, our potential function, the gradient field, curl. That's what we're going to be looking at. And let's look at that in more detail tomorrow. But I wanted to say that out loud so that you all heard it, but not so much that you were going to be thinking about it consciously. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. I'm gonna have to review this recording because I feel like I wasn't making a lot of sense today. I mean, like less than normal. I realize I'm a math teacher, and so on a certain level, I just don't make sense most of the time that I'm talking. But I have a feeling that I wasn't even making sense to me today. So, yikes. More coffee.